Right. Hello, everyone. Good time of day and welcome to this new MLIR meeting. Today, we're going to talk about typedefs in MLIR, and Mike is going to present some slides and we're going to have a discussion afterward.
All right, thanks. Yeah, so we've been looking at this in the circuit project, and I just have some examples of what we're trying to achieve and what we've tried so far and some of the pain points we've had and what we're hoping to learn. So it's really just some examples to seed the discussion. So the motivation here is our backend is spitting out system Verilog. And something that we care about is spitting out good readable outputs. This is something that people are actually going to be reading in certain cases. And sometimes it can get quite cluttered. So for example, we have the ability to have structs in this language for hardware. And this is a small example. It can have many more fields in real world hardware designs. And so you get these huge structs. And the worst part is, they show up all over the place. So like in a module, which is sort of like a function for hardware, in the inputs to the module, you have to repeat that whole type, spell it all the way out. And it shows up also in like interfaces and all over the place. So you'll get this type repeated. And for real world designs, John said it's quickly getting ridiculous. Last week, we were looking at some stuff that it was hard to read and it's not really useful for anyone. So what we're trying to do is take advantage of the ability to typedef in system Verilog. So you can, give a name to a potentially very complicated type. And then, in your interfaces, in your modules, you can refer to that by name. So it's a little more normalized and simplified. And we want, tight control over this process so that we can generate very good looking Verilog outputs. So that's what we're looking at. And, it's not really specific to hardware per se. Other systems support this notion of giving a name to a type. So that's why we're hoping to have this discussion and think about some of the ways that we can maybe share this or do this in a way that works for other groups, also using MLIR.
Yeah, I would say this is really common to AST-like things. And so what we're trying to do is we're trying to effectively build an AST-like thing and then have, a Clang-like type system in a sort.
Right. Okay, so one of the things I just want to point out is, so MLIR has this type aliases notion. I saw this in the language reference, and it's kind of what we're trying to do here. But as far as I can see, this is sort of a way to make the printed IR a little nicer. But by the time you've actually parsed this module, the name's gone. So what we're looking for is a way to actually have, as Chris said, an AST where we have nodes in the AST that represent these typedefs and we can reason about them and do things with them. So we want something that kind of looks like this though. So, okay, it's MLIR, we can add a new operation. So let's add a typedef. And we did something like that in the first draft where, you're giving a name to a type and that's what it would look like in the IR up top. And we taught the Verilog emitter to look for those and kind of build up a table of name to type mappings. And anytime it encountered a type that was in the table, it would, spit out the name rather than printing out the whole type. So that was a good start, but it doesn't really cover all the use cases we wanted to hit. So specifically, one example is if you have the same type has different names in different parts of the design. If one aspect of the design calls a 32-bit integer by one name, you want to respect that, but potentially call it by a different name somewhere else. So this initial approach of just having these nodes in the IR and sort of looking them up by type from some table, we decided against that and kind of looked at, okay, what are some alternatives to make that a little better so that we can support more flexibility and power with this. So we talked about different things. One is, put an attribute. We could have that attribute on the operation to say which typedef to use, for the type of this operation. That gets a little weird because, first off, we have to make sure that attribute's propagating. And second off, it's not clear which operations actually need this attribute. It has to do with what operations are actually going to be emitting the type at the end of the day. And, the idea that we talked about attributes was to sort of keep this out of the type system, this notion of aliasing types and all of that. And we kind of decided after some discussions in our ODMs, well, no, this is going to be a pain, but it needs to be in the type system. That's sort of where we want to convey that information. So we talked about a couple options there. One would be to have sort of a reference in the type that kind of goes and points to some Typedef node up in the AST somewhere. And another option would be to actually wrap up an inner type with sort of an outer type that has a name in it, and just have this very simple way to wrap a name around a type and use that name in places. So we started experimenting with that, and it was this last option is what I took a look at first. So it's kind of like before, where the emitter that's actually printing out the Verilog at the end of the day would kind of look for these aliases and synthetically build up this list of typedefs up top, and then spit out the right names referencing the typedefs. The difference is before, the typedef was an actual node in the IR, and we experimented with, well, just having it like this as a type. There's no typedef node in the IR that's implicit, and it's up to the emitter to figure that out and spit that thing out. And we quickly found that that's not a great approach. We really want, as Chris said, an AST where we can have these nodes in the IR and reason about them. We don't just want to, just wrapping a name around a type is cute and nice in some situations, but it's not actually what we're shooting for here. We need something a little more.
Well, it demos, but it doesn't predictably convey the names that you need in all the cases, right? Because you can have two different types with the same name.
Mm-hmm. Yeah.
Rather, the same type with two different names. That's a better way to say it. Because there's a lot of things floating around that are one bit, but they're semantically very different.
Mm-hmm. And just another thing I'll note is, when you're looking at these type alias types, we're calling them, that wrap up another type, well, sometimes you need to go and dig out that inner type. And I call that, or we have been calling that, seeing through the alias. So I'll have some slides to kind of show the different ways that we've looked at doing that. That's one of the big things we wanted to discuss here. Okay, so after this, we tried this notion of, okay, well, let's have both of the things we've tried so far. Let's put a typedef node into the IR, and then let's put a type into the type system that references it. And after some discussions in the circuit ODMs, this is sort of what we converged on. The problem that we had was when we're parsing our operations and we parse a type alias for the operations, say some operand has an alias as its input type, we need to figure out, well, what is that alias actually referring to? And we need to do that to, satisfy the verifiers, to make sure that a struct access is accessing a struct. And so basically, I kind of got stuck there, and I said, you know what, let's just get something that we can try to work. And what that ended up being was sort of this yucky hybrid of the previous two approaches, where in addition to referencing the node in the IR, I actually just copied the type, the inner type, into this type alias type. And that makes it local, which helps and makes it easy to parse and verify during parse time, but it's duplicated and it's not really what we're looking to do. So
you also get an n-squared explosion of types in your .MLIR file.
Yeah, exactly. It's all over the place, and we're trying to come up with a design that's more like this. So that's one of the things I was hoping to discuss today, is sort of, well, how do we do this? How do we resolve a symbolic reference as we parse the type?
Yeah, in npconf, I have a type that's exactly like this. Okay. And yeah, it kind of, I'm very interested in any, if you can, kind of, show that.
Okay.
Because there's a lot of things floating around that are one bit. And yeah, it kind of, I, I'm very interested in any, if you can, kind of, show that. better things. In my case, it's not really a type alias situation. It's just a reference to a declaration, effectively, of like what fields the type has, which I model as an op instead of anyway. But yeah, it's the same problem. It's like I have a type that wants to reference something somewhere else in the IR.
Yeah. And we have had something like that before to model system Verilog interfaces, where you can declare an interface and then you can reference the signals in the interface via a type that's got a sort of a symbolic reference like that. And in that case, that type only shows up in very specific ops, and we kind of just push the verification logic into those ops rather than doing it sort of as the type is parsed and verified.
Yes, that's exactly what I do as well. It's a big problem.
Yeah. And in here, we're looking to do something that really works with all ops. We're trying to do something more flexible.
Yeah, the analogy here is something like Clang, right? Where Clang, you can use typedefs anywhere, which means that like we have an and op, right? And so and should take a built-in integer, but it should also be able to take a typedef.
Right.
Alex on the chat mentioned that this concept of named type reminds of the LLVM name struct. I don't remember how we support them, though. I don't know, Alex, if you can speak up.
Yes, so we support them as a sort temp. So you have a name, and you always have the exact struct body, so it tends to explode. So if there's no name, it's an opaque struct. And the problem I've ran into when designing those is that LLVM has type aliases, but those are local to a module, and MLIR types are local to a context. So if we were to have LLVM style type aliases, we would need somehow to make the type system in MLIR be aware of modules, and that was not something we really wanted at the time.
Interesting. Well, thanks for that. Okay, so here's what we're trying to get to. I mentioned that we were going to talk about sort of how to see through this type alias. And this is something that is key to making this work well and support these typedefs ubiquitously throughout. So there's a couple approaches we discussed. For one, we looked at sort of how does Clang do this? Because that's kind of been, as Chris has been saying, our motivation. It's like, well, okay, we have this AST, let's kind of treat it like that. So, you can't just say anymore, is this MLIR type is a struct type? That's no longer going to work because we have, well, it could be a struct type or it could be an alias for a struct type, for example. So what we did was we put some of these helpers, which Clang calls, canonical types helpers on the sort of the base type class in our type system, where we can query it. Is this a struct type, or get this as a struct type? So you kind of have these ISA and cast helpers for each type. And that's, my understanding of how Clang was doing it from reading the internals documentation. And then, Chris had some feedback, say, why don't we make a little improvement on that and kind of come up with an ISA and a caster that are, instead of having all these named methods on the base class, we can have sort of a templated caster that knows how to do the same thing. And in either approach, what we're going to have to do is sort of recursively go through every alias and say, well, give me your actual base type, and kind of melt away all the aliases and condense it down to the actual type we're talking about.
Well, the implementation of canonical types is effectively every type that can be sugared. And so in the Clang sense, you have sugar types and then you have non-sugar types. But every type, whether it's sugar or not, has a pointer to the canonical type with all the sugars stripped off. If you want to do a structural comparison, you compare the canonical types. If you want to get the sugar type because you're printing it out or something, or you're doing diagnostics, then you can walk through the type without sugar. You can peel off one level. There's all that control that you get in there. But it's nice and efficient, right? Because the normal thing is you want to do a structural comparison, like for an and, like, is this an integer? Well, the way you do that is you look at the canonical type and you ask the canonical type if it's an integer. And getting the canonical type is always one pointer dereference away. And so it's simple, it's efficient, it composes very nicely.
Mm-hmm.
The downside, as Mike says, is that you now get two type tests, right? And so you have overloading word type. You have two structural comparisons. It's like, are you an integer with sugar, potentially looking through sugar, or are you syntactically an integer? And so you have to handle that. Now, all this is C++ side mechanics that really have nothing to do with the MLIR representation. This is just all, how do you deal with it once you can represent it?
Right. And the way that we would make this work, and I've been experimenting in this PR, is you get that canonical type while it's being parsed, and you can keep that cached in storage. So like Chris said, it's just a quick lookup every time you need that for structural comparisons.
Sean asked a question. He says that it seems like all the use cases are like C Typedef rather than strong Typedefs that create like new type, something that creates a new type. So that's what we're talking about right here, Sean. But actually, this whole discussion is much more general, right? The real form of the question is, how do you have type declarations? And so
yeah, that's what I was thinking.
Yeah, the Typedef is just the first declaration that Mike is talking about here, because that's kind of in his critical path. But it's, in the AST mode, you want to be able to say, I have these declared types, and then they're nominal, they have names. And so, I want to be able to refer to those nominal types. And this concept is far broader than types, right? This notion of being able to declare and then reference something is a pretty common thing, and we use symbols for that, right? And this is one of the reasons why Mike's going to be talking a lot about symbols and the challenge of them.
Right. Okay, so speaking of symbols, we've been trying to figure out, where does this live? How do we actually set this up in the IR? And what we tried first is, what you saw before, where there's just this operation living alongside all these other things. The problem here is our modules have names. They're like functions, so they're symbolic. And we might be getting conflicts between module names and symbol names of different typedefs. So we decided, okay, we'll come up with one symbol table that can live at the top level and have this kind of unique name that's essentially a reserved name. Nothing else can be named like that. And we'll stuff all our typedefs in here. And we can use some helpers to go look that thing up and dig into it to get out typedefs when we need them. But one of the things we discussed about that is, how are we going to know that that thing has been parsed by the time we get to parsing the type? If there's a typedef, down at the bottom of the file, and we parse a type, alias type, as we're calling it, that's referring to something that hasn't been parsed yet. How do we look it up? How do we do things like cache that canonical type and run verifiers for our ops? So one of the things that Chris tossed out, this
is all about, like, how do we get the MLIR parser, the ASM parser, to cooperate?
Yeah.
And I mean, it's getting the C++ API and the structures to wrap up is all pretty straightforward. It's really about how best to compose into the existing ASM parser stuff.
Mm-hmm. Right. And so we were trying out this sort of wrapper operation, I think last week or 2 weeks ago in one of our ODMs where we were talking about this. Chris was brainstorming, well, maybe we can put these attributes as attributes on the top level module. That's interesting, because I think that we said the attributes get parsed before the body. Maybe that can work. Is that a bad idea? I don't know. So these are the things that we've been trying and what we've been looking at doing. So just to kind of wrap back up and summarize, like, what we're hoping to get out of this, we want something that looks roughly like this and, produces the Verilog that we want. So we're hoping to have, a node in our AST that can represent this C-like typedef, and a type in our type system that can reference it symbolically.
Yeah, actually, can you go back to the previous slide? Right?
Yeah.
So one of the things we're trying to do is we're trying to say, if we encode all the types as attributes, and so at the top level you have a mapping table between string name to type. Maybe that will simplify things because they're always in a global place. You can always, when you're resolving them in the IR, you can always zip up to the top of your IR region tree and things like this. The problem with that is that now you lose a lot of the value of MLIR, right? This is really not about typedefs, as Sean was saying. This is about type declarations. And so one of the types we wanted to be able to define are these interface things, which is a crazy ass Verilog thing. But the point is you want to be able to declare these types, and the natural way to do that is as operations, right? So shoving everything into an attribute hierarchy is like re-encoding things as JSON, which is not really the goal here. Furthermore, all the types are recursive and can refer to each other and things like that. So,
do you folks have use cases that require sort of context independently, having the type sort of be able to verify something about itself? Because what Alex pointed out is basically, currently the types are unique in the context, but it's in principle possible to have two modules that each have an at my struct, so then the actual type, hardware, struct at my struct is going to be ambiguous between them.
Well, this is one of the reasons why it's not super appealing to just have loose strings floating around. But yeah, I mean, if you have two conceptual MLIR modules, the overload of the word module is really unfortunate, by the way. It's very confusing.
Yeah.
If you use like the top level MLIR modules and you have two of them, then they can have two different circuit designs. They can have two different things named foo, right? And so you need to keep that straight. Right? They're not unique globally or something like that.
Yeah, I guess it's like if you were to try to compare the types across those modules, like I don't see an easy way to, in MLIR at least, for the at my struct in two completely separate MLIR module ops to be.
Oh, I thought they resolved the type, Sean. If it's like canonical types, right, you have to have the other one already resolved, I think.
Okay.
Yeah,
exactly.
So
you always have the pointer to the canonical type, right? So the type definition is like not only the name, but also the pointer to the struct or to whatever it's pointing to. So even two types that are named foo in two different modules, unless they point to the same canonical type, they would be different.
And so the canonical type contributes to the hash of the MLIR : type. Okay.
Yeah, but now that's also one of the challenges for the ASM parser here, right? Because to be able to create the IR node and unique it, you need to have the canonical type, right? So you can't actually have recursive types. There's no way to do that. The way Clang handles this is that you have effectively 4 declarations of structs, right? And so you struct foo semicolon, and then you can refer to foo star 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 star, and then you can define struct foo in terms of struct foo star 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 star, right? So you declare the type and then complete it. So I mean, we have to figure some of that kind of stuff out. I don't think that Mike's to that point. Fortunately, hardware is not recursive generally, so it's like so there's certain things that make it a little bit easier in the short term. But the general form of the problem has that kind of stuff going on.
Yeah, definitely focused on the simple form, just to make a big complex struct more readable or things like that.
And perhaps one question. I mean, so is the need to have these type 1s shared between different modules, is that sort of a requirement? I mean, to give an example, what I've done with the shape function library is I have an attribute on the module that says these are the shape function libraries of the module, and inside of each of them, it's assumed to be, it's verified to be unique. So the name mapping has to be unique. It's verified, on a module, but there's no, effectively there's no sharing. It's sort of localized.
Yeah, I think so. So why don't you keep? So the one of the big problems we've struggled with is that symbols are really close to what we want. They're just not good enough. So and another problem is I don't know very much about how symbols work, so which is one of the reasons we're here. Do you want to dive into that a little bit, Mike?
Yeah, I think so. I mean, I guess this slide has it because that's really one of the things that we were discussing last week and kind of when we were saying, all right, let's take this to the broader group and see what they think about this, because you know, when you're parsing this symbol, you know, parsing the type, and you've got the symbol and you're ready to go figure something out. I want to go get the canonical structural type so I can run my op verifier. How do you do that? You know,
and also you mentioned earlier you have to decide whether you care about that type decals being below the uses of it. And I think that we're fine with saying it just has to be the top. You know, it's fine to. It just has to be above any references. I think that's simple enough, and it's fine.
Yes. So I think symbols are going to be a problem for that. I mean, so there's a notion of scope here, which is important. And the way we design symbol is to associate them with a trait on operation. If an operation has a symbol, define a symbol table, then it defines a new scope for symbols. There's a limitation in symbols is that you cannot reference above from a non-closing operation that define a symbol table. So if you are inside a nested module or something nested inside a module that define a symbol table, there's no syntax that allows you to reach out of it directly. And also symbol is kind of a single namespace, right? Like you would collide your type name would collide with the function name if you were to reuse just symbols like this.
If you look at his example here, that's what Mike's trying to solve by making the type name scoped underneath this typedef thing.
Yes. What this slide doesn't show is how you would use them inside the module then. Would you still use a symbol reference to reference them?
Yeah, like a nested.
Yeah. And then like the symbol, because there is infrastructure in MLIR to work all the uses of a symbol. And so if you had function in this module that would be called mystruct, then you would look up all the uses of this function inside the module. If there are operations that are using the typedef mystruct using a symbol name, that would collide. I'm not sure if I'm very clear here.
I mean, on that, I'm less worried about that because the give me all the uses of symbol stuff is just an IR walk anyways.
Yeah.
Right. It's not better than that, and so we can have a different IR walk if we needed to do.
Exactly. All in all, I would say all in all, symbols are just some attributes with a convention. It's a string attribute which has a different attribute type, right? Which is this symbol ref. But if we were to introduce something for types, it seems fairly straightforward to introduce a new kind of symbol. It would be type reference instead, or typedef reference instead of symbol reference, because there's nothing in MLIR that caches those symbols or that look them up other than the symbol table. But I think when someone uses a symbol table, they intend to use it for something different than the type lookup.
Wait, so a more general form of that is you're saying like symbols could have a namespace identifier, kind of like pointers have an address space. You're saying that you could have, I'm symbol foo in namespace 4, and then you could say look up foo in namespace 4, and then you'd ignore all the namespace 3s.
But I mean, so we do already support referencing nested, right? I mean, that is just a convention, but it is supported to reference get symbol foo inside foo bar inside bar X. I think that there is this cascading already that we have. We can't go up today.
You cannot go up. You can only go down.
Yeah, I think
which for an AST is the opposite of what you want in general.
Yeah, and I think also like we want something with a little bit different, like something somewhat fundamentally different, because like, for example, we have a helper for like rewriting symbol uses, and this, if like the symbol name and the canonical type have to like have this coupling to each other, then that kind of breaks all the invariance, plus the fact that I don't know how we would even have that function properly rewrite everything. I guess it's just I think it's like Mehdi said, it's like just a string with a set of surrounding conventions. So you could totally implement my symbol ref batter that has exactly the behavior you want, and
and Jack mentioned something important, is that symbols are designed so that you can reference things that are nested below, while I think it's exactly the opposite of the role you would want for typedef. You would want to be able to reference something that is defined above, not below. It's like a typedef that is defined somewhere nested shouldn't impact the outside environment, while symbol works exactly the other way around. But again, the symbol infrastructure is very just convention driven, and a symbol ref is a very simple attribute. So creating new type of symbols, we would have to call them something different, right? But and find a new syntax for them. But that would be fairly easy to do, I think, and not intrusive in MLIR. Except that I think your kind of symbols would have to be taught to the ASM parser, likely.
Yeah, I can see that. I think that makes sense. So yeah, I mean, that definitely sounds like an avenue to explore here. You know, it's, sorry, go ahead.
I'm interested to hear what River thinks of this as well.
I'm a bit worried about duplicate symbols because, well, to a certain extent, they're just attributes. That was also like 2,000 lines of code written to manipulate them. So if we have multiple attribute types, I would rather not have like 10,000 lines of code doing effectively the same walk, but with a slightly different name. Although, if we're talking about nested, I could see uses for nested type things. If you are calling a function in a nested module and you have to have some type convention or something, that could be useful. I don't know. I mean, I guess the only major difference between this and symbols, I think, is that this has a type attached to it, right? And you're not replacing by name, you're replacing with a full thing, like, because you want to replace with the thing that has the result type already, right? So, I mean, I think that's the only difference for me between that and what we have right now with symbols. Well, and up references, I guess. But if we added a new attribute type, I think we would encounter the same problems as we do with symbols right now, which is just how they work, I think.
What do you think about the visibility, though? Like the fact that the nesting works the opposite way between.
I mean, I think visibility is still the same, right? You would still want some type aliases to potentially be private.
I'm not talking about visibility attributes. I was more talking about the scoping, right? Where you can reference symbol down the enclosing hierarchy, right? You can reference symbol nested down, but you cannot go up in the enclosing of regions. And it seems to me that with Typedef, you would want the opposite of that.
I mean, so the reason why I don't see the same is because I've heard a bunch of people complain about not being able to reference up with symbols right now. So if we're talking about like concrete user need, it's similar in a way in terms of visibility. I guess the other one, like I thought you were talking about visibility in that you don't want to have them conflict. Like if you have a function symbol, it shouldn't conflict with a type symbol. That's the same thing.
That's the namespacing, I would say.
Yeah, I mean, this kind of reminds me of when we first added symbol tables and we were talking about adding namespaces within symbol tables. It feels very similar. I think the only reason I don't think normal symbols would work even if we added up references is because it refers to a type. And maybe what we do is have a metadata attribute on symbol references. I don't know, but I think it's complicated. As for, I guess, I think your harder problem is going to be the parser, because I don't really see a lot of the parser stuff being easy or fun. I mean, I don't like the second option because it kind of assumes that, like, I don't want to really bake in API that is like, here's an API that only works if the parent operation happened to do this in its parser. That gets a little weird. I think it also isn't clear. I mean, I missed the first 10 minutes, sorry, but I think it also isn't clear that, or something that hasn't been made clear is that when you're parsing, your parent operation doesn't exist. So you can't get it because it hasn't been created yet. It's only created after the fact. So if you're parsing something in the middle of a hardware module or whatever, the thing that you're parsing doesn't exist, the hardware module doesn't exist. We just have a bunch of things that are in progress for it that are kind of just building the state.
Is that true of the top level MLIR module as well?
So technically no, but that's more of just like providing an easy way to destruct things. It's not necessarily something you can rely on.
Yeah, that's what I thought too, but Chris disagreed. He said that the previous IR, like if we had a type decals section, that you could reference it in the parser to get the type information, the canonical type information.
Yeah, so the only reason why you could get a top-level module is because we use module as a container to destruct things easily.
Yeah.
But the way that the parser is constructed is that you can actually parse, like you can give the parser a block and just parse operations into it. So there's no like built-in assumption that there is a module op at the top. That is mostly a MLIR op / parser thing.
Yep.
And we changed that such that module op doesn't have to be the top level thing.
It doesn't have to, but I think in Circuit we actually do guarantee that everything lives within a module because our hardware modules need to live in a symbol table. And so we use the top level MLIR module as that symbol table. So we do, I think we do say that they have to be within a module, even though that's not necessarily required.
Right.
But again, it sounds like we would be relying on something that's maybe like more of an implementation detail than rather than, you know, for sure we can trust that we're in a parsed module that already exists.
Sorry, I missed something. Why does it matter that we are in a module?
Our top level functions are these hardware module things.
Yes.
And I haven't shown it here, but they actually have a symbolic name. So they need to guarantee that they're in some sort of symbol table. So we use the MLIR module as that symbol table. We could have come up with our own wrapper, I think.
But
just as
where does it matter for the types?
Oh,
for the type defs.
It doesn't matter for the type defs necessarily. I was just mentioning that, you know, we don't have to use a module, as River was saying, but in practice we do. Anyway. So, you know, there always is a module op around our circuits in this world.
I mean, that's fine to assume. I think the only thing you can't assume is that my top level thing exists. Because you could be in a module, and the top level module is not your module that you want to scope things to.
Yeah.
Yeah, actually, Mike, how much of your use case actually requires a recursive structure? Like, you know, going back to the Clang use cases, maybe like an extremal situation, but, you know, you can have a type def that's, you know, at the top level, then another one inside the, you know, a class, and another one inside the method. And so then really this whole thing becomes, you know, even more complicated because it has to, it's not just like a flat parser thing. It's like, oh, like, you know, interacts with all like the deferred method parsing, and all that crazy stuff that Clang has to do. And so, the Typedef can be at the end of the class, but you use it in a method in the middle and stuff. How much of that do you have here, or is your kind of Verilog structure that you're producing just one flat module? Or sorry, modules is ambiguous, like one flat, top level declaration place thingy.
Yes, I think so. It's a little more restricted. I'm not super brushed up on the spec for Verilog Typedefs, but in general, we have to have declarations before uses, like as you read the module top down.
Can you have a Typedef in the middle of the analog to a function?
Yes, I've seen that at least. So I think you can do that.
But it sounds like in your use case for just outputting pretty Verilog, it's less of an issue. So you can always hoist it.
We want to just hoist them all up to the top of that file, or even there's a way to put them into a separate file that's kind of like headers for Verilog that you can include. So yeah, we would try to just have them all collected somewhere nice. That's
the best practice in Verilog.
Okay. Yeah, so I mean, this definitely seemed. Yeah, I think this more general case with arbitrary nesting and having it in the middle of functions, that sounds really, really hard. But this use case sounds like it's maybe tractable.
Even in a module, we have to decide, like, if you had a new Typedef operation and you insert it between two functions, like, you have to decide, is this like in the IR, is it top down, like this Typedef only impacts function that will be listed after it?
Oh god.
Or not.
Right.
Yeah, that's a tricky situation.
Yeah, and that's where, Verilog has a very specific way of looking at that, where, yes, it affects everything below, but nothing above. Is that the behavior we always want? Maybe that doesn't generalize. So, I mean, these are the questions, right? Like, kind of looping back, we're trying to figure out the main thing is, can we have this way to reference something from the type, and as we parse it, resolve that reference? That's one of the key questions we're still grappling with. And then that also ties into this, what we've been discussing of where do those things actually live? So I don't know. One of the things we discussed was from the parser, what can you get access to? Can you get access to the block that you're within, and what else is in that block? Or can you get up to the top level module and check things there? And it sounds like
you can get to operations that have been already parsed, which is everything that appears before, but not necessarily that is on closing you, right?
Right.
The operation that is on closing you, you're still parsing the region that is nested under, as River said earlier. But all the operation in the same block that appears are in the, like, you can go before in a block. Right? So that's why a Typedef operation is already parsed when you start parsing other operation later, right?
Is that an implementation detail, or is it something we can rely on long term?
It's a good question. It's not documented, but
I mean, I'm thinking if MLIR ever wants to get into parsing in parallel, it could be an implementation detail that we shouldn't rely on.
On the semantics perspective, it becomes kind of weird if you rely on the relative order of operations in a module that is otherwise containing unrelated operations. So I would expect something like a typedef list to be placeable anywhere in the module, even after it's first used, which is the case for symbols, for example.
I think it might be useful to think about this sort of as two layers. And I'll use the analogy of like SSA formation. So like when you're Clang, you parse a bunch of, plus, minus, things like that. And then you end up emitting, IR that's sort of using mutable variables for that stuff, because that's what's sort of convenient to emit. And then we run an SSA formation pass that, gives us U-step chains and all that good stuff. And I think there might be a useful way to think about this problem, to be like, can we this isn't like immediately useful, I'm just throwing this out there. But like, let's say we were trying to implement Clang with this, Clang might first parse into create MLIR ops that are more of a kind of like a meta level above, like they just have names, and like we don't have the equivalent of U-step chains, like pointers to canonical types and stuff. And then we actually run a pass that transforms the module into the form of where it resolves all those things and stores all the canonical types, and then that turns into sort of like a somewhat different representation. And then
front ends actually do this. It's called name lookup. Right? You parse into an AST, then you do name lookup and resolve the namespace scope references and all that kind of stuff.
Does that happen like on the fly in all cases, or because I think that's really what we're trying to introduce here is like basically name so I think
it depends. It depends on the language. So Swift, for example, has contextually looked up identifiers like this .foo syntax, and so. Yes. And so the identifier it refers to depends on the type context it's in. Mm-hmm. And so the way that works in the AST is you have an unresolved symbol reference expr or something, which just contains a bare string. But then when you do name lookup, you then type in French, you then resolve it to a declaref expr pointing to the declaration.
Yeah, okay. So this is, it sounds like kind of the front end requirement.
Okay, so let me expand out the question for a second here. And sorry, I missed Toyma's due to a call randomly. So is this all about the .MLIR parser? And second question is, the MLIR parser is currently trying to be one pass, but really failing at it. At what point do we make it a two-pass parser? And because if you make a two-pass parser, tons of stuff gets easier. Like right now, for example, there's this goofy. It's not goofy. I should be nice. It's this complicated logic for handling like lazy bound locations and attributes and things like this, which also are kind of forward reference, but then emitted at the bottom of the file, things like this, and a lot of that kind of stuff gets way easier if you have a multi-pass parser. Now that's perhaps complicated given that MLIR allows you to have user-defined syntax, and we can't run the parser rules and stuff like that. But maybe what we need to do is just impose some structure on it and say that, okay, well, if you have a left brace in your op definition, it has to be balanced with the right brace. And some simple policies like that would go a long ways here.
I don't think multi-pass works for every attribute. If you're parsing an unknown dialect attribute, I don't think multipass is going to work in that situation, because you would have to keep the structure around and then resolve it later. So then the multipass only applies to top level IR entities.
Well, the reason multipass helps is if you have, so generally what you're doing is you're picking up one set of name associations and creating, it's like, think about a recursive type, like you're picking up the declaration of the name and then later you fill it in, right? And so you're getting those two passes and exposing it to the things you're parsing.
If we only parse the aliases, I suppose, on the first pass, and then parse everything else the second pass.
Right, well, or just like you create the type names. And so anyways, this is just an idea. It's not a fully formed idea.
Yeah, I think you're right, Chris. I think this really does, because I think from the C++ data structure side, we kind of have some grasp on what we want this to look like.
To have a pointer to canonical type, that's quite simple. This is really all about how does the MLIR parser compose correctly, and And how does it work with the C++ infra for the parser? Which is not easy, right? I mean, this is one of the challenges of having an extensible parser like we do, right? So,
I think another, while we're talking about kind of crazy ideas, someone, I don't know if it was you, Chris, threw out the idea of a module with 2 regions and maybe having the type declaration type stuff in the first region and then all of the, the body as we normally have it in the second region. So
yeah, that gives you the advantage if you have a different symbol table, right? So each region gets its own symbol table. It has certain challenges with the current implementation, and that right now only the first region and an op get scanned for symbols for one. Easy to fix if you want to. But the other problem with it is that then module op, like MLIR : module op, now has to be changed to have this, which seems kind of weird.
I mean, could it be like a new, module with type declarations op,
Well, I'm actually a little bit confused or out of date on this. I think that the parser generally tries to push a module op at the top level of the hierarchy regardless, is my understanding. I don't know if that's a bug or a feature right now, but if you do what you're saying, you'd end up with another module op wrapped around it.
So, I mean, I said this earlier, but the fact that there's a module at the top is only during parsing to make things destruct nicely. But there's no requirement at this point that there is a module up there.
Okay.
At the very, very top.
Well, I think the parser, like the C++ function, returns an owned module op or something.
You can actually return anything. You can actually give it a block to fill up with operations.
Oh, that's cool. Okay.
So there's a lot more freedom now than there used to be a while ago. But I think the problem is that I think I mentioned earlier is that if you're in a module inside of a module, your parent is not going to be constructed. It's not going to exist at the point where you're parsing the child operation. So you couldn't assume that your parent is going to be alive at the point where you're parsing the child. Because fun custom syntax and all of that stuff. But I mean, I don't think adding the second region, I mean, if we were gonna expand namespaces, I think it would be more interesting to feel out the thing that Mehdi and I talked about 2 years ago, which is a symbol table can have multiple namespaces inside of it. And symbols can say which one they're in or something like that.
So this is like I'm a symbol foo in namespace 4 or something, and then 4 is a magic number, or what? How does that work?
A namespace could have been a string or an identifier, right? It would have been at the time what we were thinking was like it can be different accelerators or different domains like that, and you can name them. And you say I have like a module define 4 symbol tables, or you can always say like I want to add a symbol table on the module with an attribute that you put on the module saying like symbol table namespace, which is a list of the namespace that this module declares. And then the symbol reference would always have would have an optional maybe namespace, and there would be a default empty one.
Yeah, that would actually be useful. I've hit that multiple times, or like in TF save model, there's basically like 4 different namespaces that you have to track, and then in pcomp I have a use case where there's at least 2.
I mean, there are workarounds for that. You can just add a prefix.
Yeah, that's exactly what I do, but
Okay.
That's not exactly the the most.
But I don't think that the namespace collision problem is really the core issue here.
Yeah.
The namespace, because again, we could add prefixes too, right? I mean, so there you go. The broader question is how do we do that lookup at parse time so that your hw.typealias turns into the right thing? Now, extrapolating from River's point, right? The sv.typedef or the container for it that exists at the top level, it's a peer of all the users. It's not a container. Right? And so if we make it so that we can find that pure object that has already been parsed, maybe that's good enough.
I mean, conceptually, yes. I think it could be fine.
Or maybe the top level gets special cased and the parser has privileged support for looking at things that have been parsed at the top level or something like that.
I mean, I suppose we could do it where it's like find parse symbol or look up parse symbol from, or already parse symbol from where you are, to really like constrict the API there. Because, yeah, I mentioned earlier when for the random idea on one of the other slides for like storing it in your parent module as attribute lists, then we're kind of like, well, I hope my parent has its attributes before its region, otherwise my parser is going to explode.
Well, but we don't have to, so we don't have to solve the general case for all wonky ASM syntax.
Yeah. That's what I'm saying. Is like we should know
stuff you can constrain this. Yeah.
So if the constraint is just getting or finding a parse, like an already parsed symbol, maybe. Although Albert says something not at parse time.
Yeah, I mean, I had this multi-pass thing in my head, but didn't dare to say it until Chris did. But then giving it the second thought, I'm not completely convinced I understood your motivation for doing this in the parser in the first place.
I think the problem is that they have things that rely on the dependent or canonical, the other type during parse time.
But why is it during parse time that you need?
Well, so
like type inference and stuff.
Yeah.
Like that.
Well, yes. Actually, type inference is a really important one in for result types. But the other one is that the verifier hook for an and, right, wants to say, hey, the type has to be an integer, right? And so if
if you say inference or verifier, that seems to me like a separate pass that comes after parsing. Anyway.
No, the parser needs to know the types for all the opposites parsing. That's built in right now to the MLIR parser. This now,
that's right.
Incidentally, like this is a thing a 2-pass parser would allow you to get rid of.
Exactly.
Which would be pretty awesome because MLIR is quite verbose, and so
well, I mean that's a clear
get rid of all the types
for multipass.
Yeah, get rid of all the types on all the uses, right? Which has mixed readability impact, right? Because it's very nice to say dump this one up and be able to understand what it does, right?
Right. It's very useful.
So this is maybe a dumb question, and actually we're out of time. But could you have it just like this typedef at my struct or something? Exclamation point hardware.typedef at my struct, and then parse that, but leave the canonical type null, and then kind of have a second. Just have like a hook on your module that you can your hardware dot enclosing namespace thing, not to use module, but hardware dot enclosing namespace thing that then the parser just calls and it walks all the types in the IR and populates the canonical.
I have to jump off, but one of the goals here is to eliminate an invalid state. So if you admit the state where the canonical type hasn't been resolved, and now all the verifier hooks everywhere have to be aware of that, it just there's a ton of complexity on a lot of stuff. Sorry, I have to run. But
all right, we should definitely follow up on this.
Yeah, I think we probably need more conversation about this.
Yeah, for sure.
All right, we can always continue on discourse and meet next week to follow up with a live discussion as needed.
Yeah, sounds great.
Yeah, sure.
I will keep experimenting.
That's an interesting topic. Thank you, Mike, for the slides and for the introduction in the subject. It was very helpful.
Yep, of course.
Thanks everyone for the good discussion, and see you next time.
Take care.